Now we would be coming back to the lesson. In Tuesday's lesson, we have been talking about momentum, and we have basically covered most of the topics in the linear momentum as well as the collision. So I guess you could hear me. I will just keep on talking. The idea of the linear momentum, can anyone hear me actually? Yeah, okay. The idea of the linear momentum is that you have various techniques to predict the motion of the objects. For example, we have, of course, in the case of a constant acceleration, you have the kinematic equations. Without knowing why the object moves, we just know that by observation, there is a constant acceleration, so we could predict the motion of the objects in the subsequent time and locations. On the other hand, after we learn about the Newton's laws, we know that objects would accelerate due to the presence of a net force, net external force. In that case, we would be able to predict the behavior of the objects according to the force acting on them. Of course, you could have a varying force, but we are simplifying our cases in most situations by considering a net constant force sometimes. Constant in the sense that the magnitude may not change a lot. For example, in the circular motion, we have objects moving in a circular orbit, and then we would have the force direction keep on changing. It is always pointing towards the center of the circular orbit. Later, we have another property that could be used to describe the motion of the objects, and that is the energy. When you have a force acting on an object, there will be work done. And the conversion of energies from work done into either kinetic or gravitational potential energy or elastic potential energy, that could be used to predict the motion of the objects. And in the process of energy conversion, some of the energies would be lost, for example, due to friction or due to the changes in the internal structure of the objects, or maybe due to the generation of the sound or heat. These are non-retrievable energies, and they are kind of difficult to calculate. So we have come up with another tool to predict the motion of the objects, and that is based on the Newton's third law. You have the Newton's third law, which considers an effect of internal forces. In two objects, if there is one object, say 2, that provides a force on object 1, equally there would be a force on object 2 provided by the object 1, and the two forces are equal in magnitude but opposite in direction. That is the Newton's third law. So from the Newton's third law, we could derive that a physical quantity called linear momentum, which is remaining constant over the whole process. And here we need to make sure that there is no net external force acting on the system. All the forces are internal. So when would this occur? This occurs when you have, say, collision of objects or hitting of the objects by one due to another. There will be action and reaction pair. So we have various examples in the lecture notes. And the change of the linear momentum, we call it the impulse. The change of the linear momentum is the impulse. The rate of change of linear momentum, which is the rate of change of impulse, is the force. According to Newton's second law, force is actually the rate of change of linear momentum. And there are various ways in which you change the linear momentum or you provide an impulse to the objects. You could do it slowly. So delta T is large with a relatively small resultant force, or you could do it very quickly with a very large force. This could be visualized from the picture at here. If you are providing an impact, you are providing an impulse that occurs on a short time, the force would be large. So if you have a car colliding on a wall, you might think that it is good to keep the car in the original shape. It is not. Because the collision time is small, force acting on the car as well as the person inside would be large, and that would be fatal in some cases. On the other hand, Japanese cars, you like it or not, they damage quite a lot during the collision. But in that way, at the expense of the car, you protect the person in the car. And we have described two important cases of a collision, the elastic collision and the inelastic collision. Most of the time, the collision would be inelastic. And of course, you have a special situation of a perfectly inelastic collision where the objects basically get stuck together after the collision and they move with the same velocity afterwards. In the case of an elastic collision, on the other hand, you have the objects that do not get stuck together and the momentum as well as the kinetic energies, both of them are preserved. So that is an important message at here. Let me try if I could maximize it. Yeah. So the momentum is conserved in both cases, but the energy is conserved only in the perfectly elastic collisions. So we have to derive the equations for perfectly inelastic collision as well as for the elastic collisions. For the elastic collisions, after some manipulation of the terms, you could derive the formulae for final velocities, particle 1 and particle 2. Once again, I would not recommend you to memorize these equations. If necessary, we might actually ask you to derive them rather than just remember the important equations. Well, of course, I know students are very hardworking these days and they memorize everything. Well, I hope you know that we are not having a history lesson, we are having a physics lesson. So understanding the concept is actually much more important. So we have a couple of examples talking about the collision problems that is combined together with energy conservation. The important message is you need to analyze the problems according to the processes. Say in this problem, you firstly have the objects that are colliding on one another. So there is an initially collision problem. You apply the conservation of a linear momentum. And then after the collision, it becomes a single system and you could apply the conservation of energy. You cannot do it in the other way around because during the collision process, you lose energy as an internal energy loss, for example, due to the embedding and due to the heating. So that is something you have to be very careful. And in the lecture notes, we also have a topic about, let's see, collision in the two-dimensional way. We have a collision in a two-dimensional manner. the idea of a two-dimensional collision, although it looks scary, but you could always treat it just like the case of a projectile motion, in the sense that you could always resolve components of the motion into two perpendicular directions. The two perpendicular directions are independent of one another, so you could apply conservation of linear momentum in each single direction and solve the problems. So in this slide, you could see that before the collision, you have an object M1 moving with a V1I from left to the right, and M2 is stationary. In general, it will have a velocity M2I. Both of them would have components of velocities x and y. And after the collision, due to the conservation of linear momentum, you could write down these two equations. Things you have to be very careful about is, firstly, you need to resolve the components of momentum. In many cases, it is equivalent to resolving the components of velocities. So here you see that in the x direction, it will be V1F cosine theta, V2F cosine phi for the x direction, and then you have the y directions. Now, you have to be careful about the positive and the negative signs. If you define from left to right is the positive x, from bottom to the top is the positive y, so something like that. If you define the axis like that, then you are having negative velocity in the y direction for the particle 2. So there should be corresponding adjustment in the equation. Or you just leave it like that, and if the calculated result is a negative value, then you know it is a movement in the y direction in a negative sense. So it is moving in a negative y direction. Right. It is always good to take a look at an example and see if that the discussions make any sense. We are not concerned too much about how we draw the angle when we are solving the problem. It is the drawing just to make some representation. At the end, the calculations would make the adjustments. Okay. Now, here you have a traffic accident that is about to happen. And let's take a look at the question. There is a car traveling towards east. So this one traveling towards the east with a speed 25 meters per second along the positive x direction. And it is about to collide with a lorry or truck traveling 20 meters per second along the positive y direction. At the end, we assume that the vehicles get stuck together, and we try to determine the direction and the magnitude of the velocity of the masterpiece for the two cars get stuck together. So the idea is you have a two-dimensional motion. So in the case of a one-dimensional motion, you know that conservation of linear momentum applies. So linear momentum is conserved. And what we are doing now is just to extend it a little bit. It is conserved in all directions. And we are trying to make this consideration by thinking about the motions in perpendicular directions, say x-axis and y-axis. and we apply the conservation of linear momentum separately in the two directions. For example, here, along the x-axis, you have the initial momentum along the x-axis initially should be equal to the linear momentum along the x-axis finally that are equal to one another. So what is the equation? Initial linear momentum m1v1I for the blue car. No contribution from the truck because it is traveling along the y direction. So zero velocity from the truck along the x-axis. Finally, both cars stuck together, so m1 plus m2 for the mass. And if they are traveling along VF direction, that makes an angle theta with x-axis. Then the velocity component is VF cosine theta. It is like this for the x-axis. What about y-axis? Similarly, apply linear momentum conservation. You have initial momentum along y direction equals to the final momentum along y direction. So what is initial momentum? m2v2I. Only for the truck, there is a momentum in y direction. No momentum from the car along the y direction initially. Finally, both trucks get stuck. So m1 plus m2 times velocity along the y direction. So VF sine theta. So two equations, two unknowns, VF and theta. For the rest, you know how to do it. That is mathematics. So you get the idea is not really considering the car 1 as a horizontal component, car 2 as the y component. It is just happening that along the x-axis, there is only car 1 initially. Along the y direction, there is only car 2 initially. You could, for example, have two cars. One traveling only along x, the other one is traveling like that initially. So that makes an angle. So you would have both x component and y component. In that case, you just resolve components. So idea, once again, is resolve velocity components before the motion or before the collision and after the collision. So here, initially, the car has only x component. The truck has only the y component. So that makes the life much simpler. And we could solve the problem by solving these two equations, 1 and 2. Mathematics, really. So I will not bother too much on the mathematics, although at the end, you need to get the right answer to get the full marks. Something I really would like to stress to all of you, when you are trying to work out the problems in the assignments, well, or sometimes the test and examination, do not just write down the initial equation and the final answer. They are steps. Steps are the proof that you know what you are doing. If you get me a right equation but the wrong answers, I'm sorry, I could only give you the marks for the initial equations. No proof for your understanding on working out the problem. So that would be very disadvantageous for students to just write down the initial equations and final answers, unless you're really a genius and can make sure that you answer the things correctly. So students sometimes like to do the things on a rough work. Use the paper, use the answer book for rough work and show us the rough work together with the final answer. calculators, we typically would not allow those powerful ones, not those very powerful ones where you could store the data or do the calculations and so on. So there are calculators list. There are calculators list that are available. Usually, it is the HK Hong Kong Examination Authority approved calculators that we would accept in PolyU. On the last, can we use M1, V1, and cosine? M1, V1, and cosine. I'm not quite sure what that is. M1, V1, this cosine theta is equal to 0 because the car is traveling along the x-axis. So it is the whole component of velocity in the x-axis. Okay. Not sure if that is answering your question. Okay. Right. I think that is not quite sufficient as an example for the two-dimensional case. So for now, I would try to take a look at a tutorial question. So if we go to the tutorial worksheet, number 2, and let's take a look at question number 8. Because the class is large, according to PolyU, we are not having face-to-face lesson. We would be doing all the lessons online throughout this semester. For the midterm, please check the teaching schedule. I would explain other concepts a little bit later. At the moment, I would be focusing on the linear momentum. So I could explain a bit later. So at here, you have 2 plugs in the question 8. The mass of the blue one is 20% greater than that of the mass of a green one. So you have a green one. Maybe I can magnify it. Okay. So you have a green plug, and then you would have a blue plug. And this one has a mass of 1.2 m, maybe. This one is m. And before the collision, the plugs approach each other with equal momenta, but opposite in direction. With an equal magnitude of momenta, but opposite in direction. And so if the green plug is approaching with a velocity v, and you could consider that the blue plug is approaching with the velocity magnitude that is equal to, well, basically v divided by 1.2. Because at the end, the linear momentum of the green plug is equal in size but opposite in direction to that of the blue plug. So you have this setting at the beginning. Before collision, the plugs approach each other with momenta of equal magnitude and opposite directions, and the green plug has an initial speed of 10 meters per second. So simple. Now v is equal to 10 meters per second. So this one, the blue plug, is actually moving with 10 divided by 1.2, so it's around 8.333 meters per second. Try to keep a little bit more steps, a little bit more accuracy, because when you proceed with the calculations, you have the accuracy that you have the errors that accumulates. So if you use a very little number of significant figures, the final answer would be quite accumulating errors, and that may lead to wrong answers or very different from the original correct answer. Well, different people have different methods. If you could work it out, that is perfectly fine. If you multiply, you could use it. I don't mind. Actually, you could do that. And now you have the speeds of the plugs. You have the speeds of the plugs after the collision. You are asked to find out the speeds of the plug after the collision. If half of the kinetic energy of the system becomes internal energy during the collision. So what is the scenario? You have the plugs. Well, I may show you the diagram that is easier. You have the plugs. This is the green one. This is the blue one. After the collisions, of course, you have the motions that are described in the diagram. And at the same time, the kinetic energies of the two plugs after the collision is only half of that of initial value. So let us try to think about it. The plugs have to obey the conservation of linear momentum, but the energies are lost during the process. So that is something you have to be very careful about. So to save a bit of time in writing out the steps, I may just show you the solution and explain the steps of the solution. So at here, it is written for you, initial momentum of the system. It will be 0 because they are equal in magnitude but opposite in direction. So you have the 1.2 m times VBI for the blue plug, that is equal to m times 10 meters per second for the green plug. So you get VBI equals to 8.33 meters per second. The initial kinetic energy of the whole system is due to the green plug and the blue plug, 1/2 mv squared. Final kinetic energies 1/2 mvg squared plus 1/2 mass of the blue plug times the velocity of the blue plug squared. So that is the equation, at least. And this equation is equal to 1/2 times this term. This term is the one on the front. According to the question, half of the kinetic energy is lost. So that is why we have 1/2 times this term. Or we could rewrite the equation as Vg squared plus 1.2 times Vb squared. That is equal to 91.7 meters squared second squared. Notice that Vg corresponds to the green puck velocity after collision. Vb corresponds to the blue puck velocity after collision. And by conservation of linear momentum, if we are clever enough, we could actually see that in the diagram, in this diagram, the green plug and the blue plug, they are moving in exactly opposite directions. Think about it. Initially, the two plugs are moving head-on along the x-axis. They are moving head-on along the x-axis, and they are having equal magnitude of a momentum. So total momentum along the x is equal to 0. Total momentum along the y is equal to 0 because they have no velocity components along the y direction. So if that is the case, before the collision and after collision, there should be, for the whole system, 0 momentum. There should be 0 momentum for all the for the whole system, and that is why, rather than resolving the components, that here the question directly write down. The question directly write down mvg equals to 1.2 m times vb, because there is no momentum to start with. Well, for the whole system, I mean, individual plugs, of course, they have their own linear momentum, but when you add the two plugs together, there is no momentum. So it doesn't really matter which direction we consider. Here, we consider the direction along their final travel direction. Of course, you could always write down in the y-axis, you have a Vg, that is a sine 30 degrees, and that is a Vb sine 30 degrees. In the x-axis, that is a Vb cosine 30 degrees. And here you have a Vg cosine 30 degrees. That is the same. At the end, after cancellation, you still have the same equation. So Vg equals to 1.2 Vb. Solving these two, you would be able to obtain Vb and Vg. So that is the whole idea. First, you have to set out the scenario. Initially, what is the linear momentum? And finally, what would be the linear momentum? And the velocities are, of course, related to the kinetic energies. So that is how we handle the situation. By solving the simultaneous equation, we would be able to obtain the solutions for the final velocities. So that is the idea for this question number 8 in the tutorial worksheet. The condition of 30 degrees is useless only in this equation, only in this problem. Luckily, because they move in opposite directions. Both are at 30 degrees. If one is moving at, say, 30 degrees, the other one 50 degrees, no, you have to resolve the components. The 30 degree is useful in general, but here it happens that they cancel one another. Okay, now we try to finish the lecture notes first before we take a break. We would conclude the lecture note set number 1 by going through quickly the concept of the center of mass. So the idea of the center of mass is, well, to put it in words, when you are having an object that is not a point object, sometimes you would have a complication on how do I consider the forces acting on the extended object. And because in most of our calculations, we are considering objects as point particles. So if you have an extended object, when forces are applied to them, it may actually cause the turning effect on the objects. So, for example, when you apply a force about the center of mass of an object, it will cause the turning. On the other hand, if you apply the force right at the center of mass, because the two sides, because the two sides are not are having a turning effect, balancing one another. So in that situation, you would not have any turning effect. So in a certain sense, the center of mass is considering at the position of the object where you have the turning effect on the whole body equals to 0. You have most of the situation, you will not have point particles. You would have extended object. And if we assume all the forces acting on the extended object to be concentrated only at the center of mass, we could then consider as if it is a point particle and have all the forces acting on a point particle. That makes the calculation much easier. Otherwise, you have to justify whether we are having any turning or other funny effects on the object. So for the center of mass, it is calculated in this way. As I've said, the main idea is like you are considering the turning effect acting on the particles. So you could consider in this way. Suppose you have two particles that are distributed in the space like this along the x-axis only. And of course, if they have some force acting on them, they would generate some turning effect. So the idea to calculate the center of mass is to find a location in between the objects such that the turning effect generated by the separate objects is equal to the turning effect generated by putting all the mass at this location. So the idea is, let us assume that the turning is happening around the origin. So you could multiply the mass and the distance from the origin together for each particle. So m1 times x1 plus m2 times x2 plus so on and so forth. And then the whole turning effect is equal to the turning effect generated by all the masses concentrated at this point. This point is at a distance cm from the origin. So you could write the sum of mixi equals to the total mass times xcm. Of course, things are not always that simple. You may not have the particles just lying on the x-axis. You may have particles maybe lying on the y-axis or maybe somewhere in between. So the turning effect could be considered as about say here, the origin. So along the x direction, this would be the center of mass along the x direction. Along the y direction, this would be the center of mass along the y direction. Along the z direction, this is the center of mass along the z direction. So this would help you to find out the coordinates of the center of mass. And these are for individual particles. If you have a continuous distribution of the objects, then you would have to do the things by integration. Notice one thing. Here, MIXI, X is the measurement of the distance from the origin. It could be that the object M1 is lying in the negative x direction. In that case, x1 is a negative value. So the turning effect can be due to the M1 about the origin from the positive direction, and could be due to M1 in the negative x direction. The turning effect would be in the opposite sense. So if you have balanced the two sides, then you would have the zero turning effect. So for example, if we move the whole system such that the origin is now placed right at the center of mass, the turning effect due to M2 would be equal to the turning effect due to M1. This sounds a little bit strange, but if you think about it, let us replace M2 by its weight. Let us replace M2 by its weight. So we try to hold a pivot. We try to hold a pivot right at the center of mass. The turning effect by M2, which is M2 times G times this distance, x2 maybe, is equal to the effect M1 times G times x1, that is equal to 0. Because the pivot is now placed at the center of mass, and xcm in this case becomes 0. So the right-hand side becomes 0. So this is a way that helps you to visualize the effect. But mathematically, the operation is we try to multiply the mass by the distance from a certain location for all the particles. And then the center of mass is assuming to be the whole mass concentrated at that center of mass as measured from that specific location. Here, the location is the origin. And once we have obtained the center of mass, we could assume all the effects that happens to that extend the object or the system of the particles to be concentrated right at the center of mass. And the calculations would be much more simple because we do not have to deal with individual particles, but we are handling one single particle that has a total mass of the system and has the position, velocity, accelerations handled by the center of mass. So that is why we would use the concept of center of mass when we are having a collection of particles, a system of particles. And this would be somehow also related to the center of gravity, which is the place where the all the weight is thought to be applying to the object. And if you have a G that is constant over the whole mass distribution, which generally is true for all the objects not of very large size on the Earth, the center of gravity should coincide with the center of mass. So a very simple way to determine the center of gravity or center of mass, if they are equal, is that we try to hang the object at a certain location. The line in which you hang the object and goes down vertically would be the place where you would find the center of mass. So if you hang the same object in two different locations, like at here, you hang it at you hang this spanner in along the handle and along the end, there would be two lines, two vertical lines. Along this vertical line, you will find the center of mass, but you do not know which point along this vertical line. So you have to do it in another direction. You hang it now at here, so you know this intersection point should be the center of mass. In this particular configuration, you would have the moment generated by the left-hand side that is equal to the moment generated by the right-hand side. So that is why it is used to determine the center of gravity or the center of mass. The difference between the center of mass and the center of gravity is just like you are talking about what is the difference between the mass and weight. So the center of gravity is where we assume all the weight is applied to the object. Center of mass is we assume where the mass of the object is focused on. In the case where G is uniform in the space, which if you are not having a very, very large object, you have G that is uniform over the whole object, then the center of mass should be equal to the center of gravity. If your G is not uniform in the space, which, well, on the Earth at least, that is quite difficult unless you have an object extending kilometers. Otherwise, they are can be considered as identical. So they have a physical difference, but practically they are the same. Right. So at here, I would just stop the teaching on the lectures notes number 1. If you check on your Blackboard or the Learn at PolyU, you will see that well, it's not the assignment, it is just the tutorial questions. So you will see that there are tutorial questions for tutorial 1 and tutorial 2. We just work on one question in the tutorial 2. Tutorial 2 is covering the chapters 6, 7, 8, and 9. So from circular motion to linear momentum. And I would not spend further time on these tutorial questions. So I rely on you to work on those tutorial questions. And as I mentioned before, there are textbooks available on the internet or in the library, which you could find more questions to work on in case you find some topics that may be a little bit difficult to understand, or you would need to practice a bit of the skills. So you could find the chapters in the University Physics Volume 1 textbook, for example, and then you could work on it. Now, before we take a break, we would do the usual thing, as in most lessons, and that is a quick question on a U reply. So we have 2 questions to work on today. The first one would be related to the momentum. So For now, will you please take a look at the question, and we will take a break, and we'll come back to the lesson at 4:30. So you could take a short break and use the time to work on the question as well. Okay. I will take a break about 2 minutes, and if you have any questions, please leave the message on the chat area, and I will try to answer it later. Okay.
Sir, is there only one question?
For now, yes. We will
Okay.
have another one if time permits.
Okay.
Right. So the calculation of the center of mass is at here. For the calculation of center of gravity, it would just be that you are replacing the mass by the weight. So that is why if you have G that is constant over the whole space, then the center of mass should be equal to the center of gravity, because G would be identical and would be cancelled out. So the idea is we are borrowing the concept of the turning effect due to the force at around a certain point. So that is the idea of the moment, the idea of a moment or the torque force about a certain force that is turning about a certain point. So if you have a positive x, then let us assume that it would be turning around the point in the clockwise direction. And if it is in the negative x, it would be a turning effect around the origin in the anti-clockwise direction. So that is how we consider the scenario. And of course, what I've described is just a intuitive way of thinking. The mathematics is shown at here. I'm sorry, I may not be answering the private questions very quickly, because if I answer the private questions, I have to turn it on, and it is blocking the view. So I use another computer to answer the question, and that is for the questions open to all. There's only one question right now. We have some questions later, depending on the time. I'm sorry that I missed quite a lot of private questions, so I'm not sure if I could answer them all. Well, the question 9.34 is the one that we have to adjust back on. I better type the code, so you could try to write down. Yeah, it has been more than 8 minutes, and yep. Question 9.34. No, I don't think I would make a second explanation. I may just show you the equations at here, which I think I have to rely on you to revisit the videos when I post it on the Blackboard. Yes, please submit the answer now, because we have to carry on with the lesson for lecture notes number 2. Right. I think I am showing this. Yep. So if you are interested for the solution of the question we just discussed in the tutorial 2, I show the solution in the video. So you could check on it. Right. I will start again in 2 minutes time. I will start again in 2 minutes time. Okay. Now, I would explain the answer at close to the end of the this lesson. So for the time being, let us come back to the lesson. Well, okay, I'm not counting the accuracy. I would just count the participation for this test. The real idea really is not to test you, it's really to provide you some exercise. So I will explain the question a little bit later. Right. So now let us come to the second set of lecture notes. And the idea of the second set of notes is that we have been talking about the linear motion in the first set of lecture notes. So all things seems to be very good. We have particles that are under the force, and we could determine what is the motion of the object along a straight line, or even in the circular orbit. So we could determine the acceleration that is pointing towards the center of the circular orbit. But we know very well that it does not really describe all the things. It really does not describe all the things. So let us think about another important class of motion, and that is rotation. Okay, once again, we are not counting the first question's marks, so we would focus on the lesson for the time being. I do not want all the students to be really focusing on one single question. We are now moving to the second set of lecture notes. Okay, so we would be talking about another class of the motion, and that is related to the rotation of the objects. Concept is quite simple. Think about it. You have a wheel. So if you look at the video, you have a wheel, for example, and there is a certain axis of rotation. And you have the wheel that is, for example, the wheel of the car rolling on the street. This motion, of course, you have actually a collection of particles. You have a collection of the particles on the wheel. Every single particle would be moving with a different manner. For example, if you know that there is a particle on the edge of the wheel, when the wheel rotates, it would be moving faster compared with a particle that is right next to the axis of the wheel. So there are two particles. One is close to the edge, one is close to the center of the axis. So the particles on the outer edge would be moving much quicker than the particle moving close to the center of the rotation. But yet, there are some similarities in terms of the motion for the two particles. To start with, let us think about it. Say you have a wheel like the one shown at here that is stopped or stationary at the beginning. So we could always draw a line from the center of the axis to the outside. So let us call this just a reference line. In many cases, this reference line could be considered as the x-axis. But now you are not talking about linear motion. You are talking about rotational motion. So if it rotates, let us consider it rotating in the anti-clockwise direction. It rotates in the anti-clockwise direction. So, for example, there are two particles. One is at here, the other one at here. Or maybe I should redraw it. One at P and one at the outer edge. When the wheel rotates, think about the two particles which are originally on the reference line. After a certain time, they would be rotated to a new position. If you have the wheel that does not change shape, this line would be moving all together. All the points along this line would be moving all together. They would be sweeping through an angle theta. Swinging through an angle theta during the motion. This angle theta is the angle between the original location of the reference line and the new location of the reference line. All the particles along this reference line would be sweeping through this angle theta. But is it actually just for the particles on this reference line? Well, the idea is after this motion of rotation, particles originally on the reference line would be sweeping through an angle theta, but particles on other places of the disk, for example, if they are originally along this line, after the reference line has moved through an angle theta, this line would also be moved through the angle theta as well. So this rotation of a theta is not confined. The rotation of the angle theta is not confined to those particles on the reference line. It is actually true for all the particles on the disk. If one particle rotates an angle theta, all the other particles will be rotating through the angle theta as well. So there is something universal for the motion of particles on this disk, and that is the angle they sweep through during this motion. If one particle sweeps through an angle theta from the origin, other particles will be sweeping through the same angle theta during the same period of time. They are different in the sense that the linear displacement will be different, because if you have particles that are placed at here in this point, it will be at a distance r from the center of the rotation. The particle at the edge would be at another distance, for example, large r, from the axis of the rotation. So the outer one would be at a distance large r from the center of the rotation. When the reference line sweeps through an angle theta, the linear displacement during the motion for the particle P, it would be equal to S. S is related to theta by the relation S equals to theta r. That is the mathematical definition of the angle in radian. For the particle at the outer edge, the displacement, say large S, it is equal to theta times large r. It is related to the distance from the axis of rotation to the point on the particle. So the displacement is related to theta times r. So we could consider the object to be rotating in a synchronous way. They are rotating in a way that they sweep through the same angle at the same time. And if they are sweeping through the same angle, that means the angular speed, the rate in which the angle changes, should also be the same for all the particles on the disk. And similarly, the acceleration rate of change of the angular speed would be the same for all the particles. So this would be an important starting point for the discussion. Let us try to go back a little bit in the lecture notes. And the idea for the lecture notes set 2, at the beginning, it will be concerned with the rotational motion. And firstly, we would be talking about the description of the rotational motion. Remember the case of the linear motion. In the linear motion, when we talk about the linear motion, we start with what? We start with kinematics. That means description of the motion of objects, especially when you have a constant acceleration. We do not know why the objects move. We just know it moves with certain pattern. So we use kinematics to describe the motion. And then we start to understand why it moves. So Newton's law. Afterwards, it is energy. And then afterwards, it is the linear momentum. In the case of a rotational motion, we would do basically the same thing. Firstly, we would be considering the kinematics. That means describing the rotational motion of the object. And then we would consider why the object rotates. So that is related to the Newton's law of motion for the rotational motion. And then rotational kinetic energy. Finally, we would have something called angular momentum. And that would be chapter 11 of the lecture notes. Okay. Right. So here, the lecture notes number 10, firstly, we would describe what is the meaning of the angular displacement, velocity, and acceleration. And then we would introduce the kinematic equations for the rotational motion. And afterwards, we would try to understand why the object rotates. So that would be the Newton's law. In particular, we would be talking about inertia. In a linear motion, inertia is related to the mass. And in the case of a rotational motion, we will introduce a new concept called a moment of inertia. And that is related to how reluctant the object rotates about a certain axis. Mass for an object is an intrinsic property. It does not change with the configuration. However, in the rotational motion, the configuration change, that means change of the axis of rotation, for example, would cause a change of the inertia. So that is something quite tricky. And we would talk about it much more slowly. And we would talk about the energy of the rotational motion. And finally, we would analyze the rolling motion. That means the object rolls on the surface. It does not just rotate, it rolls. So there is both rotational motion and linear motion. That is a combination of both. And in our discussion of the rotation motion, we would be focusing on the objects that are rigid. Now, rigid objects, by definition, is something that does not change the shape. I have talked about it at the very beginning of the course. When you have an object that is rigid, it would be something like a disc or plate. Strictly speaking, objects are never completely rigid. They have some, if you like, elasticity. They would change the shape a little bit. For example, if you pull a wire at the end, they would just extend. If you rotate a disc, because of the need to provide the centripetal force, actually they would change the shape a little bit, but the extent of change is very small in most cases. There are, of course, exceptions, like what I have mentioned before, a pizza dough, the bread of the pizza, when you are spinning it, it would get larger and larger. So this is not a rigid object. A rigid object would not be changing a lot in the shape when it is undergoing rotational motion. So that is our assumption for many of our calculations. And we just talk about it. We would first talk about the angular position. So at the calculations, we always consider the displacement. In the linear motion, we consider the linear displacement. And in the angular motion, or rotational motion, we consider the angular displacement. Displacement considers the difference of the angle extending from the center of the rotation, the displacement of the angle extending from the center of the rotation after the motion and before the motion, the difference between the final effect and the initial effect. So at any particular time, there would be an angle associated with the object's location. For example, a particle P on the rotating disk, it can always be represented by what we call a polar coordinate. Rather than using x and y, we could represent it by r and theta. If it is a rigid object, a very important point is that if it is a rigid object, we would not expect the r to change. If r changes, the shape of the object should change, and that is not rigid. On the other hand, theta would change because it would rotate from time to time. When the object is rotating, it will sweep through an arc. The arc length during the sweeping motion is related to the theta, the angular displacement, as well as the distance of the particle from the axis of rotation r. And when we are making all these calculations, in particular, the angle, we would not be using degrees anymore. We will not be representing the angles in degrees anymore. Instead, we would represent the angle in the radian measurements. So the unit of the angle is radian. The unit of the angle is radian. In secondary school, in high school, you learn about the angle measurement. A complete revolution, one turn, would cover 360 degrees of angle. In the radian measurement, it is 2 pi radian, because by definition, an arc length of 2 pi r corresponds to one complete revolution. 2 pi r is s, and that is equal to the angle times r. So theta is equal to 2 pi when you have a one complete revolution. So 1 radian is written as 360 degrees over 2 pi, or equal to around 57.3 degrees. So that is the conversion between the angle in radian and the angle in degrees. When we are describing the angular motion for a rigid object, it does not really matter whether we are talking about the angle sweep through by the whole object or by individual particles. They should be the same if it is a rigid object. So that is something you do not have to worry about. When an object rotates by an angle theta, individual particles on the object should also rotate by the same amount. Although they may have different starting point and different end points, the difference is the same. The displacement is the same. So that is the important message. So it is the difference between the final angle and the initial angle that is the most important. This is what we call the angular displacement. So the final value of theta minus the initial value of theta. So the particle, when it rotates, it sweeps through an angle. So the difference is the angular displacement. And by convention, we would consider motion in the anti-clockwise direction as positive. It is something we take as a convention. So associated with the angular displacement, just like the case of the linear motion, we have the angular velocity or angular speed. The angular speed is defined in a similar way as the linear speed. Average value is change of the theta over the change of time. So delta theta over delta t, that is the average value. And instantaneous value is to take the delta t equals to 0 in the first equation. So when delta t approaches 0, it is becoming the instantaneous angular speed. Once again, we would take, by convention, positive values when theta is positive or theta is increasing. So in the case of the xy coordinates, when you are moving from the left to the right, it is considered as positive. And if you are considering the angular motion or rotational motion, movement in the anti-clockwise direction is considered as positive. Movement in the anti-clockwise direction is considered as positive. And similarly, increasing angular speed in the anti-clockwise direction is considered as positive. So moving faster and faster in the angular direction is considered as a positive angular acceleration, and so on. So that is something we use by convention. And here it is just the definition of the angular acceleration, the average value as well as the instantaneous value. Now, units. The angular displacement, because it is obtained by the difference of the angles. So the unit should be in radian. Once again, do not use degrees, use radian as the unit for the angles. So the rate of change of angle, here the unit of the angular displacement is radian. Here the time is second. So the unit should be radian per second for the angular speed. And for the angular acceleration, it would be radian per square second. It will be radian per square second, the second square. Something easy to figure out when describing it in the lecture notes, but when it happens in the questions, it might be kind of a messy. But we try to go through them one by one. So just a note at here, when you have a rigid object that is rotating about a fixed axis in a certain amount of time, all particles, all parts of the object, they would be characterized, all parts of objects, they would be represented by the same set of angular motion parameters. So all the particles on the object would have the same angular displacement. They would be moving with the same angular speed and also accelerating or decelerating with the same angular acceleration. So that is a very important concept. On the other hand, linear speed, linear velocity, and linear acceleration are different for different particles on the rigid body, because the angular displacement, for example, theta is related to the linear displacement by this equation times r. And then what about the angular speed? Angular speed or angular velocity it is actually equal to, well, actually related to the linear speed v. It is the angular speed, or omega, times the distance from the axis of rotation. And finally, the linear acceleration for any particle, acceleration, it is equal to the angular acceleration times r, which can be obtained by just the deviation of the equation shown at here. So S is equal to theta times R. So differentiate S with respect to t, it will be differentiating theta with respect to t times R. R should be a constant for a rigid body. So V is equal to omega times R. And similarly, A would be equal to alpha times R. That is the idea. And the direction of the rotation, as I've said, we are trying to make the thing simple. We are always looking down from above and consider the rotation in a plane. Let us try to make the thing simple first. We are analyzing the rotational motion, assuming that the particles are just rotating in the plane. So positive angular displacement is in the anti-clockwise direction. Negative angular displacement is in the clockwise direction. In terms of a vector, well, because you know that here the rotation is positive and then backward is negative, it basically refers to a vector quantity. In terms of the vector representation, it is represented by a vector that points in a direction corresponding to what we call the right-hand rule. So this is a very confusing concept for many students. Now, it is a rotation. And if you think about it, how do you represent this rotation as a vector? A clever way, or the shorthand form of representing this vector, is by means of this right-hand rule. So if you take out your right hand, let us try to show it with my face. So if you take out your right hand, the finger of the right hand is curling along the rotational direction. So the direction of the thumb would be the direction of the vector. Fingers of the right hand would be curling in the direction of the rotation, and the finger of the thumb is the direction of the vector. Now, students get very excited when they see there is a vector, which is an arrow, a straight line with an arrowhead. They get very excited. But please take note that the vector for angular displacement is actually a shorthand notation. It is actually some kind of a symbolic rotation. Although the vector for angular displacement, angular velocity, and angular acceleration is represented by this arrow, what it actually means is a rotational motion in a plane perpendicular to the arrow. So things are actually kind of complicated. In here, once again, we try to make the things simple by considering only the motion in a plane. So whether it is a positive vector or a negative vector, we could handle it simply by considering whether it's an anti-clockwise motion or clockwise motion. If it is anti-clockwise motion, that is a positive angular displacement, or omega or alpha. We are not going to the momentum yet. We would talk about it in the next unit. Okay. So in the case of the clockwise motion, it will be a negative value. So in that way, we have simplified the idea of the vector. In a certain sense, the vector in that situation is just pointing out or into the paper, because you are looking on the problem in a plane. So you are just pointing in out or into the paper. The vector for the angular quantities, they could be quite complicated in the three-dimensional case. So we just focus on the two-dimensional case for the time being. All right. So here are some hints. It is not just the omega. It could be also the theta and alpha. They would be pointing in the same way. Once again, this is just a symbolic representation. When we represent a vector, we usually use an arrow. So it is a straight line with an arrowhead. So the arrow or the vector that we use to represent, not to actually mean that it is pointing in that direction, it just use it to represent something. It doesn't mean it is pointing up or down. Separate the two things. The actual scenario is it is rotating, but we try to represent the rotation by an up or down arrow. I hope that is clear enough. It is not saying that it is rotation with up and down motion. It is rotation inside the plane. Okay. We are not using the right hand. We are just introducing the vector format. But in our calculation at this level, we just consider rotation clockwise and anti-clockwise. So do not try to use the right hand for now. If you go to mechanics, in the mechanical engineering, you would use the vector form, but here we just consider simply rotation in the plane. So considering rotation clockwise or anti-clockwise should be very sufficient. We would have some examples to show you how to find the direction of omega later. It depends on the context. So now, let us try to look at this slide first. How to handle the rotational problem. So the idea really is you try to consider rotational motion, angular motion similar to linear motion. This would makes the thing much more easier, but you have to be very clear that you are handling rotational or angular motion. You are not handling linear motion. But the good thing with this connection is that many equations that you have seen in linear motion is actually direct applicable in a certain sense, direct applicable to the case of an angular motion. So let us take a look in the situations to make it clearer. So here we would move to the case of the rotational kinematics. When you have objects that are undergoing angular acceleration, we have a set of equations that could describe the angular displacement and angular velocity if you have a constant angular acceleration. So the situation would be exactly similar to the case of a linear motion. Let's first take a look in the equations. Now, the equations looks very scary at the beginning, but once you settle down and try to look more carefully, they look kind of similar, kind of familiar to you. Because if you are careful enough, you try to replace all the theta by x, all the omega by v, and all the alpha by a, you will see that they are actually equations you have seen before. Look at the next slide. Here we try to make a direct comparison between the linear motion, the kinematic equations for linear motion on the right-hand side, and the rotational motion with constant angular acceleration on the left-hand side. Notice the similarity. They are actually identical, except that the symbols are different. Now, the equation formats are the same. Be very careful to what I say now. The equation formats are the same. The meaning of the symbols are different. On the left-hand side, they are talking about rotational motion about an fixed axis. On the right-hand side, they are concerned with the linear motion along straight line. They are physically different in terms of the concept, but because of the similarity in the equation form, that would make the life a little bit easier for you in terms of the calculation. Okay, so once we are comfortable with the equation forms, then the next thing is we try to adjust our minds so that we are no longer in the right-hand side. We are no longer in the linear motion problems. We are moving ourselves to the angular motion problems. So we are not seeing linear displacement anymore. We are not seeing linear velocity anymore. We would be seeing angular displacement, angular velocity, and angular acceleration. Okay, with that, we are ready. So let us take a look in the first example. Now, we have a wheel, and this wheel is rotating with a constant angular acceleration of 3.5 radian per second per square second. So what does it mean? It means alpha, which is an angular acceleration that is equal to 3.5 radian per second squared. And the next thing is, if the angular speed of the wheel at ti equals to 0, it is equal to 2 radian per second. So omega I is 2 radian per second. you are asked to find out what is the angular displacement, delta theta, over a time of 2 seconds. So how does it work out? You have the equation of, well, you have the parameters alpha, omega I, and t. You are asked to find out what is the angular displacement. The equation that you would need to use is the one shown at here. Delta theta equals to omega t plus 1/2 alpha t squared. All the symbols looks very alien to you maybe, but if you compare it to the case of the linear motion, you could see that alpha, well, try to, at the beginning, at least at the beginning, try to consider it as A. A is given, omega I, which is VI, and you are given the T, and you are asked to find out what is the angular displacement, which in a linear case, it is delta S. So you immediately could figure out the equation that is required. It is equal to VI T plus 1/2 AT squared. But of course, you are not working in linear motion anymore. So replace all the terms. Replace delta S by delta theta. Replace delta S by delta theta. Replace VI by omega I. Replace A by alpha. So that is how you handle the rotational kinematics at the beginning. Later, you would be comfortable enough to get rid of all this. But at the beginning, let's try to stick to the linear motion to make it easier to handle. Omega, kind of like W. Okay. So here, you try to put in the numbers. Omega I, 2 radian per second. Time is 2 seconds. So alpha 3.5. So at the end, you will find out it is equal to 11 radian. And 11 radian, if you convert it back into angle, it is, you could write it as either radian or degrees. But I would suggest you to write the value in radian, because if you have degrees, you could make things very wrong in the middle calculations. So stick to radian, I would say. But here, it is just trying to show you the angle in degrees. Now, you will notice something quite interesting, 630. One revolution is 360. So what does it mean? It means that it is rotating for more than one revolution. Does it matter? It doesn't matter. It just means that it has gone through a rotation of 1 turn plus something. So even it goes more than, even it takes more than 360 degrees, it is still okay. Okay, next question. For how many revolutions has the wheel turned during this interval? As I just said, 360 degrees is more than 1 revolution, or 11 radian is more than 1 revolution. So you just divide 11 radian by 2 pi radian. 2 pi radian is 1 revolution. So you get 1.75 revolutions at here. What is the angular speed at t equals to 0? So here you use another equation. Omega f equals to omega I plus alpha t. which in the linear case, it would be VF equals to VI plus AT. Once again, we try to make it more comfortable for you. So at the beginning, we write down the corresponding equation in linear kinematics. But later, as you are more confident with the calculations, we would not be using these equations anymore. So put the terms back into the equation, you have 9 radian per second. So that is the idea. Okay. Now,